Okay, so obviously color is relevant for us to discuss. A lot of the fundamental vision theory that we developed in terms of doing basic image analysis and so on and so forth is normally quite scalable to handling color. But there are certain aspects of color that if we actually understand the underlying properties, we can leverage the color information in a much more efficient manner. So color is important because obviously, the world doesn't exist in black and white or gray. It exists in color, and of course, modern sensors are pretty much all color. There was a time when a lot of things were grayscale, but not anymore. And color is something that people have used extensively in order to sort of convey various physical properties. Right? And our ability to perceive color is quite extensive. In fact, most of the times we really rely on our ability to perceive color, because our ability to perceive grayscale, pure illumination, is actually quite limited. We can only tell a few tens of shades of gray. But when you come to color, we have a very, very wide gamut. You can perceive a lot of different colors, but grayscale is very limited. Okay? So color becomes important in understanding how we as humans perceive the world, and at the same time, it's a truly a psychological property, right? And it's based on visual experiences. In fact, it's something that is very difficult to interpret in terms of semantic links. So, for example, you probably have encountered this all the time. When people talk about color, right, and if you bring it down to a specific color, sometimes we don't necessarily agree on what color we are talking about. So I can sit here and argue with you and talk about something that's green in color, just that it just happens that you actually don't see it as green, and you're actually calling it as something else. Now, the subtle differences in color, because they are psychological properties, can be perceived in a different way by individuals. So color truly is a byproduct of the interaction of light with something that's physical. And it's a perception as part of how your rods and cones collectively will activate themselves with respect to a particular wavelength of light. So the sensation of the color is purely a function of the brain. It's what the brain perceives, and based on that you will have a corresponding sense and an association of a semantic label to that sense, right? So I perceive yellow, or I perceive green, and so on and so forth, right? In fact, you can simulate these processes. So you close your eyes and actually press on them, you'll probably see color, right? Because it's a reaction of how your brain is perceiving that, and your brain will trigger a corresponding response to it. Now, in a more physical sense, we understand the spectrum of light, right? The wavelength of light, or wavelength of a particular energy being emitted. And in a more physics-based sense, that's how we define color. Right? We define color in terms of the actual wavelength of energy that's propagating through space and actually interacting with the physical matter. So light in general is also differentially reflected. Right? When we actually perceive the color of an object, it is now a combination of the wavelength of light being illuminated, that illuminates the particular object, the object's ability to actually take that energy and convert it into reflected energy, but as part of the conversion process, it may also offer a shift in the wavelength. So what we are perceiving is actually a combination of a particular wavelength of light interacting with a physical matter and the resultant of it. So what we perceive is relatively complex. Now, keep in mind that different material will react with specific wavelengths of light in a very different way. And it may actually result in different phenomena that typically we describe in different imaging processes. For example, fluorescence. Right? Fluorescence is something where a particular wavelength of light excites an object, but because of that interaction, the object will then emit light in a very different wavelength. Right? And the shift in that wavelength could be both either in the visible range or a invisible range, right? And generally a higher shift is typically what we associate with fluorescence phenomena. So broadly we understand the EM spectrum, right? So basically there's different wavelengths of light, energy being propagated, and for us in terms of perception, human perception, our sensitivity is typically within the range of 400 to 700 nanometers. Beyond these wavelengths, we don't really sense a whole lot. We don't gather much energy. Right? And in fact, we see a dominant amount of energy here. It's just how human visual systems evolve over time, and also because of the fact that if you look at the EM energy emitted by sun, the dominant light source for us at least, is because it's mostly within that range. Right? You do have other bursts of energy coming through, but it's fairly small. Now, if we are to look at color as a property, then we have to go back and say, well, what is then our interpretation of radiometry? Right? We have looked at radiosity in terms of illumination. Right? We have so far discussed about radiosity only in terms of pure illumination. But now, if we have to address color, we are saying that it's actually, the illumination is an integral over multiple wavelengths. So how do I break that term up and define radiometry with respect to a specific color? So what that means is almost all the terms we have looked at so far, we have to now define them in terms of per unit wavelength. So we talk about now, rather than just radiosity, spectral radiosity. Right? Radiance becomes spectral radiance, in which case we would basically look at watts per square meter per subtended angle per unit wavelength. Okay. Now, in general, almost every object, physical object, will have a particular property to absorb or transmit light. When we look at reflected imaging, right, so typical imaging where you have a luminance source, we have a camera that is actually taking in light that's reflected from the object surfaces. Over there, we truly care about what is the reflectance property of objects. And the reflectance property of objects will vary according to wavelength. So for example, let's say, you're looking at some object, you have a source of light coming in, and if I were to say, well, what is now my spectral radiance? Not just radiance, because so far we only talked about radiance of the object. But now we are talking about what is the spectral radiance of the object. So if I had to look at the spectral radiance of the object, it's a matter of saying, how does my object emit different wavelengths of light? So one can end up with what you call a reflectance profile for an object. The amount of energy the object will actually emit out at different wavelengths. For that matter, the illuminant that we have is also not something that's constant. We have to look at that now in terms of a spectral illuminant. So as a result, the amount of energy transmitted by the illuminant may be defined by an illumination curve like that. If I look at a curve like that, you can kind of see that, obviously it transmits a lot of energy at higher wavelengths as opposed to lower wavelengths. So the color signal that we are actually going to perceive is the combination of the two. You can come back to what you've seen so far in terms of pure energy being measured off of the surface of an object as being now an integral over this curve.